video. In this video we are going to take a look at what I've been working on when I'm not working on the railgun project. And this is a school project involving robotics. Basically what we have to do is we have to make a robot that can jump based on dynamics and calculations and all kinds of stuff like that. The things you would see in a educational project. And our design is going to be pretty sophisticated and complicated. That's why I was going to document the project as a side series on this YouTube channel. So as you might remember, this design over here is the concept what I originally made. It's been designed now with motors and such, but this was the original concept. It's pretty easy, or well, the mechanics is pretty easy, because basically what is happening is that there is a motor attached to this part and it will rotate, and these links, they should be shorter, which is also fixed, but you'll get the idea that when it rotates, the spring over here and here, they will be under pressure. They will be pressure, or well, they will be in an energized state, and when they are, the robot goes down, because the length of the springs will be the original length minus the displacement. Therefore there's energy stored in the springs, and when the motor continues its half cycle, because at the moment it's at this point in the fixed, or well, let me do this with another color. In the fixed concept, this is where the spring is in the energized state, because it's pulling the entire spring against this part, which is also fixed, and therefore you get this new length. Now when it goes to this part with a certain speed, it will make an acceleration, and I hope you remember that from your basic mechanics physics class, that this equation, Newton's second law, that it simply states that whenever there's an acceleration, there always is a force, assuming there also is a mass, always a mass. So when you have this acceleration, you have a force. This force pushes downward on the ground at these points, and the spring will be in an energized state. Therefore it does want to go to equilibrium at all times. Therefore, since here is a ground, it will also push on the legs over here, but since there's a ground over here, there's a ground, therefore the force will be directed upwards in the body. And again, according to this, there will also be an acceleration, therefore the robot will go up. It's pretty simple, and if I can draw it over here. So we have a body with a mass and a center point. This is our spring. So what we have here is we have state 1. It's in equilibrium, and if we take this displacement, delta, I call it delta because that's the standard symbol for displacement. This displacement will then be stored as energy, or also a force, but the energy at this moment is simply 1/2 k, which is the spring constant, times the displacement squared. And assuming this is a solid ground, so now there's energy stored, and in a fraction of time it will cause the acceleration, and it will leave the ground. The energy that's currently here represented as its kinetic energy, because it has a linear kinetic energy, assuming you don't create a angular kinetic energy, but we'll take a look at that later because it's certainly a problem. But this is just simply the main working principle, and then it comes back down. It has a certain potential energy at this point, which is represented by the mass times the gravitational constant times the displaced height of the center point of the center of mass, and it comes back down. The inertia makes sure that the kinetic energy is stored again in the spring energy, and the motor that was over here, it helps with storing energy, because obviously this isn't a 100% efficient system. That's simply not possible. Therefore we must keep adding energy to the system, where it will make a continuous movement. Now, where does this come from? You might think, well, it's actually bio-inspired, which is the theme of the project, that it has to be bio-inspired. And my design is inspired by kangaroos and jumping humans, simply because the springs will act as a knee, because you can try it for yourself. Without moving any parts you can jump. You must store energy in your feet or your knees, and this is the method we are going to attempt. Also, it has been done before. This is a robot made by Festo, which is a European German company, and they have done the same thing, but they have used pneumatic actuators, which you can see right here. Also here. In here they have the controls and all kinds of stuff. Here they have, this is the springs which they use to store some of the energy, which can then pull the entire feet back, therefore making the upward motion, as you can see here. As this pulls up, this goes down, and you create a force at the contact points. And again, the force you create is ma, where a is the acceleration upwards, meaning you will get a speed and a displacement and all kinds of stuff like that. But we'll take a look at it later, at how these equations work. So this is the working principle I explained before, which you can see again in here. This is what I drew in the concept phase. So you can see at number 1 the body as it is at rest. Here the motor pulls the ball or the legs upwards, and it comes back down, stores energy with a delta H, which is the change in height of the center of mass. Then we will use servo motors, to displace the body over here, assuming we have enough grip with the ground, making sure we don't fall over or slip. And if we do that, we come in this position, and then we release the energy stored in the springs, which will then create the upward acceleration, and then it is in a flight period and comes back down. It displaces the legs forward with a certain angle, and the kinetic momentum and energy will be stored again in the spring, because at the moment it has a potential energy and a kinetic energy, and mostly the kinetic energy will be stored again in the spring, and we will see that later. And once it's done that, it displaces again in a position where it can go again, and then it follows the routine, and then hopefully we'll make a very good robot that can do all of these things. But of course there are quite some problems, which we will also take a look at. So now we are going to take a look at some math, and what you can see here is, I see a mistake already. Okay, what you can see here is very simple. This is the equation for power when it comes to a electrical power, and V is the voltage, the input voltage, where I is the current and D is the duty cycle, because we will be using sophisticated motor controllers, which I will design myself. Therefore, that is also going to be a part on this project which I will document, and therefore the microcontroller will send a duty cycle to the motor drivers, which will give a certain P. And we also have P for the motor, where the tau is torque and theta dot is angular velocity. You might think, what is this theta dot? Well, theta dot is the time derivative of the angle theta. So for example, we have a bar, and it makes it changes its position from here to here, and it has a angle theta, which is pretty simple, and it takes a certain time to go from here to here. Therefore you have a time derivative d theta dt, and Newton wrote this as theta dot because we are using dynamics, and it's a lot easier to do this with simply a dot above the time derivative, because we will see a lot of complicated stuff, and if you have to write all of this continuously, you will suddenly lose track of what you're doing. Also, also the second derivative, which is this, is simply two dots above it. Therefore you can go easily from theta to theta dot to the acceleration, and acceleration, as you know, will give us a force. So this is how I will write stuff from now on for everything you will see, and hopefully you won't get confused by it. And I think it's pretty interesting because this is dynamics, and most of you are here for railguns and electrical systems and all that kind of stuff, but now you will learn a little bit of dynamics, mechanics, and all kinds of stuff like that. So back to the equation. As you can see, we have two equations for power, and then we will substitute P into each other, which we will get a equation voltage times duty cycle, where the duty cycle is a number between 0 and 1. Therefore this can vary from minimum to maximum, which will influence these factors, which is the torque and the angular velocity, as I said. And the torque, you can't really decide that by the voltage. You can decide the maximum because the current is also limited, which is due to series resistance from the motor, windings, impedance, and all kinds of stuff like that. Therefore, when your voltage drops too low, you might not produce enough torque and not enough angular velocity, and everything will stall. Therefore, if we make a maximum torque, which we will see later in the equation after this, we will see that the torque is a function for the angle, and at certain points it has to deliver a higher torque than at other points, and therefore if p is constant, we will also have a fluctuating theta dot. Therefore, if we visualize it in a graph and we put theta dot in the y direction and t for time, we will see a sine wave kind of movement, which is not a nice sine wave, but we will see kind of this in the plot if we were to plot this, but this is not good, meaning we will have a slower and faster times when it has to turn the motors, and therefore we will create problems for ourselves. Therefore, if we reach this point over here and the robot touches the ground, we are in a phase where we will screw ourselves over, and that's a pretty bad thing to happen. So it has to be fixed to a angular velocity, which is kind of represented by this, which is a little bit of change, but not too much, not as bad as this. So we will make it fairly constant, and we will see that the angular velocity depends on, or the angular velocity decides at what speeds we are going to make the motion.